Okay, so last week in lecture we introduced atoms and elements, right? So the basic building block of matter are these atoms. They consist of these three subatomic particles, our protons, neutrons, and electrons. And then we were introduced to all the different atoms that we have here in our universe that humans have discovered, our periodic table of elements. All right, now we're going to start taking those elements and we're going to start mixing and matching them together to create chemical compounds. All right, so when we say a compound, all right, that means that we have atoms for more than one element bonded together. All right, so again, we're taking an atom from one element and bonding it together, sticking it with an atom from another element, forming a chemical compound here. All right, and this keyword here, bonded together, this is what we refer to when atoms are forced together. So let's just talk about a chemical bond. All right, so generally speaking, a chemical bond, these are just forces that are bonding or sticking atoms together. All right, so atoms will form bonds with one another, form bonds with other atoms here. And there are two different types of bonds that we're going to look into. All right, our first is what's called an ionic bond. All right, I'm going to leave a bunch of room here to make some notes about ionic bonds, but the other type of bond that we're going to talk about are what are called covalent bonds. Whoops, covalent. All right, so our ionic bonds, these are going to be between metals and nonmetals. All right, so one of our atoms is a metal, the other atom is a nonmetal. They're going to form an ionic bond with one another. Metals and nonmetals. Remember, we looked at our periodic table last class period, and we have this little staircase that runs down our periodic table. This separates the metals on the left side here from the nonmetals on the right side, right? So if we have a compound where one element lives on the left, the other one lives on the right, that would be an ionic compound, all right? So what exactly are these ionic bonds, again, between metals and a nonmetal? So it turns out that metals, they don't hold on to their electrons very tightly. And so what happens is these metals can lose electrons. All right, so our metals, they lose electrons. All right, so if I'm a metal atom and I've lost one of those negatively charged electrons, what does that mean about my charge now? I'm left with a positive charge, right? So if a metal loses an electron, they become a positively charged ion, and we have a special name for those positively charged ions. They are cations, right? So our metal will become a positively charged cation because it loses electrons. Nonmetals, on the other hand, they hold on to their electrons very tightly. They're not going to give up their electrons for nothing, and in fact, they can accept extra electrons. So our nonmetals, on the other hand, they're going to gain electrons, and if it gains an electron, that means it's going to become what charge? a negatively charged ion, which we call an anion. All right, so then what is the bond that takes place between a metal and a non-metal? Well, one of them's positively charged, the other one's negatively charged, and opposites attract, right? That's what we call an electrostatic interaction. So our ionic bond here is this electrostatic interaction between positively charged and negatively charged ions. All right, and electrostatic interaction, that's just a fancy physics word for this opposites attract phenomena. All right, that metal cation is attracted to the opposite charge of that non-metal anion. That's what's holding these two things bonded together. Okay? So if we were going to imagine what an ionic compound would look like here, we're going to take our metal, we're going to give it a positive charge. We're going to take our nonmetal, we're going to give it a negative charge. Oops. And again, we have that opposites attract interaction holding these two things together. All right, bonding those two atoms to one another, or more correctly, those two ions to one another. Okay? Cool, so whereas ionic bonds will take place between metals and nonmetals, covalent bonds will form between nonmetals. All right, so these occur between only nonmetals. All right, now remember those nonmetals, they hold on to their electrons very tightly. They really like electrons. So what happens when you bring two nonmetals together is they start engaging in this tug of war over these electrons. One of those atoms really wants that electron. The other ones also really want that electron. And that tug of war is what's holding those two atoms bonded together. All right, so we have this key word that we're going to have synonymous in our mind with a covalent bond, and that is the sharing of a pair of electrons. All right, or a shared pair of electrons. And that sounds a little bit too nice and neat, like they've got this cooperation going on, but again, really they're both in this tug of war. They're both trying to pull that pair of electrons onto themselves. All right, and that's what's keeping that pair of what's keeping those two atoms bonded together. Right? So tug of war over that electron pair. All right, if we were going to imagine what a covalent bond looked like here, then again, we're going to start with our two atoms that are bonded together. All right, but now we're going to have to draw this shared pair of electrons. So this atom has its electron cloud. This atom has its electron cloud, but they're also sharing this pair of electrons between them. All right, again, this is what categorizes or characteristic of a covalent bond. We have our shared electron pair. Okay, that's what's keeping those two atoms bonded with one another. All right, so step one, we need to be able to categorize a compound as being either ionic or covalent. All right, what type of bonds do we expect to see? So I'm going to pull up a periodic table here. All right, the first one I'm going to start with is CO2. All All right, I'm going to start with this here because I'm pretty sure that everybody has an idea just from existing as a human being in this day and age what this molecule is. What would we call this? Carbon dioxide. All right. So first of all, is carbon dioxide an ionic or a covalent compound? Covalent. And what gives it away? They're both nonmetals, right? So carbon lives over here on the nonmetal side. Oxygen lives over here on the nonmetal side. So this is indeed a covalent compound. So this is just an example of what we would call a chemical formula. All right, so before I go on, let me just explain what we see here. Our chemical formula tells us in our compound what elements are present. So I can see from my chemical symbol here, I have this uppercase C for carbon. I have this uppercase O for oxygen. So those are my two elements that are present. It also tells me the ratio in which these two elements are present, or how many carbon atoms I have, how many oxygen atoms I have. All right, that's what this little subscript down here is telling me. This is telling me that there are a total of 2 oxygen atoms in this compound. All right. Likewise, it also tells me how many carbons there are. In this case, there's nothing written here. All right, that means that there's how many? Just 1 carbon atom. We omit that subscript if there's just one of them. All right, if there's more than one of them, we would have to state how many there were present in that compound. All right, so carbon dioxide consists of 1 carbon atom covalently bonded to 2 oxygen atoms, right? And again, I know it's a covalent bond because both carbon and oxygen are nonmetals here. All right, cool. So given our compound formulas, let me go ahead and just reset this. All right, we can say we said CO2 was an example of a covalent compound. All right, I'm going to put down a few more formulas, and you're going to tell me whether these are ionic or covalent compounds. All right, NaCl, what do we got? Ionic, because if we look, sodium lives over here on the metal side, chlorine lives over here on the nonmetal side. Metal and a nonmetal means we have an ionic compound. And what about MgCl2? Also ionic. Magnesium actually wasn't very creative, lives right next door to sodium. All right, chlorine again being a nonmetal, so this is an ionic compound. And what about C6H12O6? So this is a covalent compound. Remember, even though hydrogen lives over here, it's kind of out of place. Hydrogen, remember, we have to remind ourselves, is an exception. It is a nonmetal despite living to the left of that staircase. So all of these are nonmetals, making this a covalent compound. All right, all you bio majors, what is this the chemical formula of? Anybody know? It's a sugar, yeah. It's specifically glucose, or one of those 6 carbon sugars, but yes, it is indeed a sugar. Cool. All right, so step 1 is given a compound formula, we need to be able to figure out whether it's ionic or covalent, all right? This is important because what we're going to learn how to do next is how to name these compounds. And how we name them is going to depend on whether we're talking about an ionic compound or a covalent compound. We have different rules depending on which one of these 2 classes it sits in. So this is step 1. Given a compound formula, we need to figure out what rules we're following, ionic compounds or covalent compounds. All right, so let's get into what those rules are. We're going to start with what I think is the harder of the 2, and this is our ionic compounds. All right, and really before we can sort of dive into naming stuff, we got a bit of work to do first. We got to build up our tool chest here and our ability to talk about these compounds. All right, so first of all, an ionic compound. This is a compound that's held together by those opposites attract ionic bonds. All right, so an ionic compound has ionic bonds, meaning an ionic compound contains a metal and a nonmetal. All right, that's what we've established thus far. Okay. All right, so next thing we're going to learn about, and we'll tie this back into our discussion of ionic compounds here in a second, but we need to first define what a valence electron is. Right? A valence electron in an atom is its outermost or highest energy electron. Electrons. All right, so out of all the electrons in an atom, there's a subset of those electrons that we denote as their valence electrons. Those valence electrons, they're both like physically the most outermost, so they're the most spread out in our atom, but they're also the highest energy of our electrons. They are the most important in understanding the chemistry of an atom because these are the electrons that participate in chemical bonding. Right? Whether we're talking about an ionic bond or a covalent bond, it's the valence electrons that are involved in that bonding. If we remember back to our discussion last week of the periodic table, we said that there was a logic behind how the periodic table was arranged. That elements that lived in the same column, in the same family, they had the same chemical properties. Well, and we didn't even talk about what those properties were, right? We just said if they're in the same column, same chemical properties, all right? Well, one of those chemical properties is number of valence electrons. All elements that share a column have the same number of valence electrons, all right? So, elements in the same column have the same number of valence electrons. All right, last class period, we learned, given our blank periodic table here, we talked about a few different ways in which we could cut this up. Kind of the same idea. So given a blank periodic table, we want to be able to look at an element and be able to figure out how many valence electrons it has. All right, it's really straightforward here. It turns out that everybody in this first column has one valence electron. Everybody in the second column, what do we think? How many valence electrons? 2 valence electrons. Now, the one little tricky thing is I am going to skip this block in the middle here. What do we call this block? Our transition metals. So we're going to skip over our transition metals. We'll kind of revisit them here in a little bit. Turns out that they're a little special with regard to these valence electrons and the charges that they form. But moving on, skipping transition metals, boron's family has 3 valence electrons. Carbon's family has 4. Nitrogen's 5, oxygen's 6, our halogens, what do we think? 7, and then our noble gases have 8 valence electrons. There is one exception that we're going to note, and that is helium. All right, zooming in on helium, if I have a neutral helium atom, how many electrons does it have? 2, because it has 2 protons. So helium's an exception. It's just so teeny tiny, it's small of an atom, it can only have those 2 valence electrons. All right, so we're just going to note this is an exception, which I wrote way too big. has only 2 valence electrons. All the other noble gases have 8. Okay. So now again, we're talking about ionic compounds, right? We'll get to covalent compounds here in a bit. We're restricting our discussion to just ionic compounds. And remember, in our ionic compounds, our metals are losing electrons and our nonmetals are gaining electrons, all right? So it turns out that our metals, so now specifically talking about ionic compounds, oops. All right, our metals are going to lose all their valence electrons. When they become ions. So, since the number of valence electrons corresponds to our column here, that means that when these elements form charges, everybody in the same column forms the same charge of ion. All right, so again, my first column here, these metals have 1 valence electron. If they lose that valence electron, if they lose that negatively charged electron, what's their charge going to be? +1. All right, so everybody in this first column here will form ions with that +1 charge. All right, because they lose their valence electrons, they each have 1. That gives them 1 fewer electron than proton, giving them that +1 charge. What about my next column? These all have 2 valence electrons. What's the charge going to be if they lose those 2? +2. All right, what about my next column here? And this is now specifically talking about my metals in this column, really specifically aluminum. All right, what would the charge of an aluminum ion be if it lost all 3 electrons? +3. All right, now, in our discussion of ionic compounds, we're actually going to ignore this column here. Carbon doesn't really form ions. Silicon doesn't really form ions. You see these elements a lot when we're talking about covalent compounds, which we'll graduate to. But discussing ionic compounds, you won't see those 2 elements, all right? So we're going to skip over those. But now we're in the nonmetal side of our periodic table here. And remember, our nonmetals, they're going to gain electrons. All right, well, how many electrons are they going to gain? Our nonmetals gain electrons until they have a total of 8 valence electrons. All right, so they're going to add a bunch more until they get to that total of 8 valence electrons. Okay, so just going to our periodic table here, let's look at nitrogen's column. Nitrogen has 5 valence electrons. If it's going to add electrons till it gets to 8, how many is it going to add? It's going to add 3, which is going to give it a charge of -3. All right, oxygen's family here. Oxygen has 6. It's going to gain 2 more, giving it a charge of -2. And then our halogens, they all form ions with a charge of what? Halogens, remember, being fluorine's family. All right, they're going to form a charge of -1. All right, and then what about our noble gases? They're happy. They already have 8, which is why they don't appear in compounds. All right, they don't form bonds with other atoms. They have already gotten their 8 electrons. They're not going to lose any. They're not going to gain any. So these do not form ions. All right, you will always only see them as neutral atoms. Okay? And we'll talk about this a little bit more going forward. It turns out that this transition metal block in the middle that we skipped is because our transition metals are a little weird, and they can form ions of any charge, all right? You can't tell just by looking at the periodic table. So we'll have kind of a special way to deal with them. But all of our other columns on our periodic table, based on where an element lives, we can figure out what the charge is going to be. Remember, metals form positively charged ions, nonmetals form negatively charged anions. Okay? All right, well, we'll practice that here in a little bit. We're going to lay down one more skill, and then we'll sort of roll it all together here. Okay? The first thing that we need to do is, given two ions, we need to be able to build our chemical formula. All right, and let's just note that we're talking specifically about ionic compounds. Importantly, these rules do not apply for covalent compounds, so we want to have these two in separate bins in our mind. Okay, so I'm going to leave some room up here to make some notes, but I just want to sort of put an example down. All right, we're going to take sodium and we're going to take chlorine. All right, and we want to put these together in some compound. Sodium, however many I have, chlorine, however many I have, right? We're going to build one of those chemical formulas for this compound here. All right, so first of all, our rules for these ionic compounds. Okay, we're going to make a note at the top. This is the one thing that we want to have kind of embedded in our brain when it comes to this process, is it's all about the ion charges. You got to look at the charge on those individual ions in order to put these formulas together. All right, that's because our compounds, our ionic compounds, must be neutral. That is to say that their net charge is equal to 0. All right, the other thing we're going to note about these formulas is we always list that cation first, then our anion. All right, you can't switch it up. It would be incorrect. Okay, so first of all, I already kind of did part of that already. I made sure to list my positively charged metal first and my anion second in my formula. But now I got to figure out how many of each of these I have. And again, it's going to correspond to the charges on these ions. So everybody take a second. Look at your periodic table. What charges do I need to put up here for sodium and for chlorine? Sodium lives in, what family does sodium live in? What do we call that first column? Our alkali metals. And that first column there, they all form ions with a +1 charge. All right, whereas chlorine is a halogen, our halogens form ions with a -1 charge. So sodium's +1, chlorine's -1, put them together, that would make a neutral compound. I have just as much positive charge as negative charge. So we want 1 sodium for every 1 chlorine. But again, if it's a 1, we just omit it altogether. So my chemical formula here would be NaCl. Importantly, chemical formulas, let's just make note, we got no space in there. All right. All right, let's do another one. Let's do potassium and oxygen. And again, everybody's going to take a second and figure out what my sign is, or rather what my charge is for my potassium ion and my oxide ion. All right, potassium lives in that same family as sodium, one of those alkali metals, so it's got a positive charge, +1. And what about the oxide ion, the oxygen's ion? -2. It's got those 6 valence electrons. It gains 2 more. And again, my goal here is to build this chemical formula. I'm going to list my cation first. I don't know how many I need. Followed by my anion. Not sure how many I need yet. All right. So my goal is to make a neutral compound. So first of all, I think this is a simple enough example that we can probably look at this. What should my chemical formula be here? K2O, right? I'm going to need 2 of these positively charged potassium ions to account for that -2 charge on my oxide ion. All right, we have a clever little trick that we can use to get these numbers, which is called the swap and drop method. All right, by that I mean I'm going to take that charge on my anion, that 2, I'm going to swap and drop it down. All right, likewise I have a +1 charge on my potassium here. I'm going to swap it over, drop it down. All right, this is just this little trick that we can use in order to get our chemical formulas. Importantly, they mean different things depending on what position they're in. When the number is in that upper right-hand corner, we're talking about the charge on that ion. When I do my swap and drop, this is no longer a charge, right? When it's a subscript down here, it's not telling me the charge on my potassium. What is it telling me about my potassiums? That I have 2 of them, right? It's telling me how many I have. All right, so importantly, these numbers mean different things depending on our position. This is just a little trick. It's just a little trick to make sure that your charges are nice and balanced. All right, I'm going to do another one here. I'm going to have you guys do this one on your own. Aluminum and sulfur. You're going to fill in our charges here, and then you're going to give me the chemical formula for this compound. All right, what should aluminum be? +3. And what should that sulfide ion be? -2. All right, so now we're going to do our little swap and drop method. This 2 is going to swap, come down here. So I have 2 aluminums, and I have 3 sulfurs in this chemical formula. All right, my swap and drop here. Okay, there's one more rule that we need when we're putting together our ionic compound formulas. All right, those subscripts cannot share any common factors. All right. So much like fractions, we need to make sure our chemical formula for ionic compounds are fully reduced. And I'm going to make a special note here so that we don't get tripped up. This is only for ionic compounds. This rule does not apply to covalent compounds. All right, so what do I mean by this? So let's do another example here. Let's do magnesium oxide. Magnesium, if we look on our periodic table, that's our alkaline earth metal. That has a charge of +2. Our oxide ion has a charge of -2. So if I did my swap and drop method, I would get Mg2O2. All right, but now my two subscripts here both share a common factor. All right, what is that common factor? 2. All right, so in order to get my actual chemical formula here, I need to take out that common factor, meaning I'm going to divide both of those subscripts by 2, leaving me with just MgO. Put a box around it, final answer. All right, that's my fully reduced chemical formula for that compound. All right, cool. So given two elements, we can look at the periodic table, figure out what the positive charge is on my metal, what the negative charge is on my nonmetal, put them together in such a way that we cancel out all that net charge and make sure that that formula is fully reduced. All right, so now we're ready to learn how to name these ionic compounds. Okay, and the first thing that we got to do is actually learn how to name the ions themselves first. So we're going to first learn how to name our cations. All right, our cations we're going to divide into two camps. We're going to call the first one our type 1 cations. These are the ones that we've been using thus far. Type 1 means that you can determine the charge by looking at the periodic table. All right, so restricting ourselves to cations specifically, that means that we're skipping these transition metals in the middle here. We'll talk about how we deal with these transition metals here in a second. Right now we're focused on the ones that we know based just on their position, where we know the charge based just on the position on the periodic table. And this is kind of best case scenario. These are the easiest to name. So for example, let's actually just put some examples. Na plus. All right, if we have a type 1 cation, it's simply the element name plus the word ion. All right, so Na plus, this is simply the sodium ion. All right. Mg plus 2. What would this one be? The magnesium ion. All right. Note on our periodic table, we do have the names of our elements given. Okay. So very straightforward to figure out what our ion name is going to be. I'm going to leave some room right here because I'm going to complicate things in a little bit, but I first want to introduce our next class, what we call our type 2. All right, and in contrast, unlike our type 1s, this means that you cannot determine the name based on the periodic table. Cannot determine the charge All right, and so again, this is going to correspond to our transition metals. All right, so what makes transition metals tricky is there's no rhyme or reason between what type of ion a given transition metal will form. So for example, iron you will find very frequently out in nature as having a +2 charge. All right, but there's also iron that you will find frequently in nature with a +3 charge. All right, so our transition metals can adopt any charge they want. They're always going to be positive because they're metals, so they're losing their electrons. But as far as y'all are concerned, it could be any number. I will say you'll never see something above 7. That's crazy. All right, it's not going to be like +52 or something nuts like that. But nonetheless, they can adopt any positive charge that they want. You can't tell just by looking at the periodic table. So because of that, we have to build this charge into the name of these ions. All right, and we're going to do that using Roman numerals. All right, that means iron with a +2 charge is an iron 2 ion, whereas iron with a +3 charge, this would be, I believe in y'all, iron 3. All right, so then everybody take a second and name the following ion for me. All right, what do we got? This is titanium. 4 is IV. Titanium 4 ion. All right, again, the Roman numerals corresponds to the charge on that ion. All right, now I said we're going to leave a little bit of room here because there is a group of type 1 ions that are also transition metals. And the reason why we classify them as type 1 is despite the fact that they're transition metals, you only find them in nature in one charge state. All right, so if we go to our periodic table here, I'm going to get rid of all these little markings. We're going to call these our type 1 exceptions. All right, the first, it kind of isn't an exception, but it's helpful to lump it into this category because it helps us find the other two, and that's our aluminum ion. All right, and we already discussed aluminum has these 3 valence electrons, so aluminum will form a charge of what? When it loses them, +3. All right, and the reason why I say it's helpful to start with aluminum is because the other two are connected here in this diagonal. All right, so these are our 3 exceptions that we just have to know the charge of. All right, they're only ever found in nature in one charge state. Aluminum is +3. Conveniently, it kind of goes in order here, whereas aluminum is +3, zinc is +2, and silver is +1. All right, so this little diagonal of 3 elements here we just got to note is our exception to our type 1. So this aluminum +3, Again, zinc is +2, and silver is +1. All right, so even though, so this would be the aluminum ion. All right, and then this is the important part to note. Because zinc is a type 1, we just got to know it's got a +2 charge, and we don't build that charge into the name. It's not a zinc 2 ion, it's just a zinc ion, because all zinc ions have a +2 charge. All right, so again, just something we have to have memorized. Aluminum's +3, zinc is +2, and my silver ion, not a silver 1, but just a silver ion, has a charge of +1. Okay? All right, so we just want to go back to our notes here. As I said, we left a little room for these exceptions. Aluminum, zinc, and silver. All right, cool. So now we got our naming of our cations down. All right, just the element name for type 1. If it's type 2, it's the element name followed by that charge information. All right, now we're going to learn how to name our anions. All right, when we name our anions, we take that element name, but we're going to smush in there this IDE ending. All right. This is a little bit tricky because exactly what letters we take off and replace with IDE depend on the element itself. All right. The good news is we have a very small amount of our anions, right? So if I just want to like clean this up for a second. All right, like we said, we're not even going to pay attention to this column right here. And we're specifically talking about our nonmetals, so I get to avoid these metalloids. I'm also going to avoid my noble gases in my discussion of my anion names. Why am I avoiding noble gases? Because they don't form ions, right? So I don't have to worry about naming my anion of a noble gas. It's not going to form an anion in the first place, right? So I'm really restricting myself to quite a small amount of elements here on our periodic table, all right? So what we're going to do is we're just going to make ourselves a little bit of a cheat sheet. This will be helpful for you when you practice, and then by the end of it, after you do a bunch of examples, it's going to be second nature as to what these names are. They're just going to sound correct. All right, so just kind of going in order of what we saw on our periodic table. Nitrogen and phosphorus live in the same family. If these form anions, what's the charge of those ions? -3. All right, so this would be a nitride ion. So nitrogen becomes nitride, and phosphorus becomes phosphide. Or again, I'm taking that element name, but I'm smushing in this IDE ending here. All right, likewise, oxygen, sulfur, and selenium all live in the same family. That family forms ions with a -2 charge. All right, I've been saying these already all class period just so that they start to sound familiar, but just to kind of formalize it here, oxygen, when it forms its negatively charged ion, we call it an oxide ion. Sulfur will form a sulfide ion. and selenium, a selenide ion. Again, all having that IDE ending. Boom. And then lastly, we have those 4 halogens, fluorine, chlorine, bromine, and iodine. They all form ions with what charge? -1. All right, so fluorine, and actually this is pretty systematic since they all end in INE, you just replace that with IED. IDE, there we go. So fluorine becomes fluoride, chlorine becomes chloride, bromine becomes bromide, and iodine becomes iodide. Right, again, all sharing that same IDE ending. Okay, so now let's put this all together here. We learned how to name our cations, we learned how to name our anions. Now let's name our ionic compounds. All right, so in our naming here, now we've gotten to our ionic compounds themselves. All right, and naming ionic, if you know how to name the ions, naming the compound is very straightforward. All we do is say our cation name plus our anion name, and we drop the word ion. All right, so if I'm going to do this here for everything rolling everything together that we just discussed here, right? Given sodium and chlorine, I can look on my periodic table and figure out what these charges are. This is a +1 charge. This is a -1 charge. And that's how I put my chemical formula, NaCl, together. All right? And then we discussed how to name these ions. This was the sodium ion. And this is the chloride ion. So when we put these together to name our ionic compound, we're going to say our cation name, followed by our anion name, and we're going to drop that word ion. So this is just sodium chloride. Cool? We get the name of the game here? All right, so I'm going to put down some elements rather. All right, so something like Ca and Br. You're going to tell me the charge. You're going to name these ions. All right, you're going to put that formula together. And then you're going to name our actual ionic compound. Calcium is +2. Bromine forms an ion with a -1 charge. This would just be, since calcium's a group 1 ion, this would just be the calcium ion. And bromine forms what ion? The bromide ion. All right, so if we're going to put these together, we're going to drop those words. I guess actually let's do our formula first. Okay, my calcium, I do my swap and drop. I should only have one of them. My bromine, my bromide, do my swap and drop. I need two of them. So CaBr2. And what would the name of this compound be? Calcium bromide. Cool? All right, now let's get some group 2 or some type 2 elements in there as well. All right, so we're going to do chromium and oxygen. All right, for oxygen, I can make you figure out what that charge is based on the periodic table, but chromium, I got to tell you, right? Because our type 2 transition metals here, we don't know just by looking at. So I'm going to tell you we got a +3 charge. All right, but same idea. Give me those same pieces of information given these two elements. All right. So chromium, I told you it has this +3 charge. Oxygen has a -2 charge if we look at our periodic table. All right, if we're going to name this chromium ion here, what's its name? Chromium 3. Right? We got to put that Roman numerals indicating the charge since it is a type 2 ion. And oxygen forms an ion, and we call it a oxide ion. All right, so putting these together here, we're going to list our cation, then our anion. We're going to do our swap and drop method. So this 2 comes down here. I have 2 chromiums, and then my 3 comes down here. I have 3 oxygens, right? So here's my chemical formula, and this is the chemical formula of what compound? What would we name this here? Chromium 3 oxide, right? Remember to put those Roman numerals in the name here. So chromium 3 oxide. All right, let me just sort of note convention here. You'll sort of see this both ways, although now especially with databases and the internet, the convention is to not have a space between your metal name and its charge. All right, but we do want a space between our cation and our anion. So that's how we would put this name together. All right, doing this last example here, sulfur forms an ion with a -2 charge. We call that a sulfide ion. All right, titanium, if it has a +4 charge, we did this one. This is titanium 4. All right, when we put these two together, cation, then anion, we're going to do our swap and drop here. So Ti2S4, and I'm done. Now, what do we got to remember for our ionic compounds? Any common factor needs to be taken out. What common factor do 2 and 4 share? 2. So I can divide them both by 2. This brings me down to just Ti1 or TiS2. All right, remember our ionic compounds, those formulas have to be fully simplified. And then the name of this compound here would be titanium 4 sulfide. Cool? All right. So last skill that we need here. All right, and this is sort of a much more practical application. We want to be able to convert from the formula to the name or vice versa. All right, and you already gave me both of those pieces of information above, so it seems like it should be relatively straightforward, all right? The key here is to make sure that you're thinking about the charges on those ions. Remember what we said at the very beginning when we were talking about putting our compound formulas together, all about the charges, right? If you're not thinking about the charges on those individual ions, you're not going to put your formulas together or you won't name it correctly. All right, so let me just put some examples down here. If I give you the formula, you're going to give me the name. And if I give you the name, you're going to give me the formula. All right, so these top two are going to be a little bit easier than the bottom two, and that's because these top two correspond to type 1 ionic compounds, whereas these bottom two correspond to type 2 ionic compounds. All right, so naming a type 1 ionic compound is kind of best case scenario because all you need are the two element names, right? Nothing fancy has to be built into the name. All we need to know is that Li stands for lithium, and F, fluorine, becomes the fluoride ion. So lithium, fluoride, done and done. All right. When we're putting the compound formulas together, now all of a sudden we have to do a little bit more thinking because, again, it's all about the charges. All right, so I want to go to my periodic table here, and I want to find strontium on my periodic table. This tells me that strontium is going to have a charge of +2. Likewise, I'm going to find selenium, or my selenide ion, has a charge of -2, and I need to consider those charges when I'm putting my formulas together. All right, so for this one, we're going to have to take a step back and first note that our strontium ion has a +2 charge, and our selenide ion has that -2 charge. All right, we're going to do our swap and drop, and then we're going to fully reduce our chemical formula here, so we get SrSe, strontium selenide. All right, I'm going to save this one for last here because this is kind of worst case scenario. So let's first do our manganese 2 nitride. So first of all, just note the chemistry gods are a little brutal. Not only do we have an element magnesium, which is one of our alkaline earth metals, we also have manganese, which is spelled dangerously close, but not the same thing. Manganese is one of our transition metals, and this is telling me that my manganese ion specifically has what charge? +2. And my nitride ion, this one I just got to know by looking at the periodic table, has a charge of -3. All right, I'm going to do my swap and drop. I get Mn3, N2. All right. Now, before we move on to the next one, because this is where people super get tripped up, but let's just note here, manganese 2 nitride contains 3 manganese ions, right? The 2 in the name is not telling me how many are there. It's telling me the charge on those ions, and then in order to figure out how many are there, I have to do my swap and drop method. All right? A lot of people will see manganese 2 nitride, and tell me that it is Mn2N. That is not what that Roman numeral of 2 is telling you. All right, again, the Roman numerals is telling you the charge on the ion, not how many there are in your formula. Don't get that mixed up. That is a very common sticking point. All right. Cool. So now keeping that in mind, I know that this molecule here is going to be copper something chloride, but I don't know what, right? And I'm going to have to work backwards to figure out what that charge is. I don't know just by looking at the periodic table. That's why we got to build it into the name in the first place. So I'm going to have to infer what that charge is based on that compound formula. All right? So how am I going to do that? Well, let's keep track of all of our positive charge on one side and our negative charge on the other. And in this formula here, I have a positively charged copper ion and 2 negatively charged chloride ions. All right, what's the charge on each of those chloride ions? -1. So then what's the total amount of negative charge I have? -2. And in order to be an ionic compound, it's got to be neutral, which means I have the same amount of positive charge as I do negative charge. So how much positive charge must I have? +2, which means that my copper here has to have that +2 charge. All right, so in these problems here, if you have a type 2 formula, you're going to have to work backwards to figure out what the charge is on that ion. You don't know what this charge is just by looking at the periodic table. Fortunately, we always know our anion charges, right? That I could find from the periodic table. Considering how many I had, I knew that my copper had to counterbalance with that +2 charge. So this here would be copper 2 chloride. All right. Again, not telling me how many coppers I have in my chemical formula. It's telling me the charge on that copper ion that makes up this compound. Cool. All right, we will pick up with that next class period.